Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to Lewis structured drawing. We did a whole bunch of Lewis structured drawing on inorganic molecules. Let's look at a few carbon containing molecules. So this is some very simple structures, and you can see they're basically mostly like neutral molecules, and that's what organic molecules are. There may be a couple of acids thrown in here and there, but for the most part they're neutral. Do we have different rules for drawing Lewis structures for organic molecules? No, because Lewis structures go by the rules here, and so that's what we're going to do here. Let's look at some of these structures and come up with a octet diagram for that. All right, well, octet fulfilled structures. Okay, C2H6. How do we go about doing C2H6? Follow the rules. Add valence electrons, place least electronegative atom in the center. Carbon, hydrogen, they're about the same electronegativity, but hydrogen cannot be a central atom, so carbon's the central atom. And if you have multiple carbons, like here you have 2 carbons, then try to make it as symmetric as possible. And then you follow the rules, the valence electrons, bonding electrons, and then lone pairs, and then try to make octets. If you cannot, then try to make double and triple bonds, and try to make sure they're all neutral formal charges. Same rules as before. Let's go about the first one here, C2H6. So here we have 8 and 6, 14 electrons for valence electrons. And so here's a carbon and a carbon, so try to make it symmetric. And that's 2 here. And we'll put the hydrogens on there, 6 hydrogens. So to make an octet for this, you already have 2. We can only put 6 more. And there you go, C2H6. That's the simplest organic molecule. It's called an alkane. You're going to see a lot of these. So then we have 2, 4, 6, 8, 10, 12, 14. So there's no lone pairs. Bonding electrons 14, lone pairs 0. We're done. Moving on to C2H4, valence electrons are going to be 8 and 4, 12. And so we're going to put the carbons again, symmetric. And then we have here 4 hydrogens. Let's try to distribute them as evenly as possible, just to be fair and not partial to any one of the carbons. So make them equal. 2, 4, 6, 8, 10. There you go, 10 electrons. We got 2 lone pairs left. Well, 2 lone pairs and 2 carbons. What do? Should we put it here? Should we put it here? Well, let's see. Go down, minimize formal charge. So instead of if I put 2 here, this will be -1 and this will be +1, which is not that great. So we are going to move it inside and make a double bond. That's called an alkene. Moving on, 8 and 2, 10 electrons, 2 carbons, distribute them as evenly as possible. You only have 2 hydrogens, 1, 2. And so there's going to be 6 over here, and we got 4 electrons, lone pairs to play with. Do you want to put them like that? That's really not a good idea, because this is to do the formal charge. 1, 2, 3, 4, 1, 2, 3, 4. It looks okay, but then you are not going to have an octet here or here. So therefore, in order to have octets, you got to have at least 2 more bonds here. So we can take that and make it into a double bond. And also that's going to only then give you 6. And if you put that also over there, you are going to have then 3 bonds. That's an alkyne. All kinds of stuff happening over here. Let's look at it. Now, the CC bonds, which one do you think is going to be stronger? Well, it's pretty obvious, I think. If you have 3 bonds like that, it's going to be really hard to break them, right? I mean, that's almost impossible. 2 bonds, yeah, you can, but it's not easy. 1 bond, snap, you can break it. So that's kind of the concept here. Let's look at the numbers here. Bond length and bond strength kind of go together. When you have 3 electrons overlapping, the nucleus and the electrons get really close here, and here you're going to have a shorter bond. Whereas here it's going to be a lot longer, and that's going to be sp3, so you're going to have a longer bond, and so you'll be having a lower bond strength. So bond length, so let's do for hydrogen and for carbon here, and we can compare them. So bond length and bond energy. Bond length is going to be in angstroms, and bond energy, so you take 2 of these electrons, bring them together, and the amount of energy that comes off is going to be in kcals per mole. Usually it's kilojoules per mole, but the one I found was kcal per mole. And so let's look at the carbon-carbon here, and bond length for this is going to be 1.53, and bond length for the double bond is going to be 1.34 angstroms. Triple bond 1.18. This is the CC. What about bond energy? Well, this is going to be 88 kcals. This is going to be, what would you predict? Smaller bond, stronger bond. So it's going to be more, and that's what it is, 152. And this is a lot more, 200 kilocals per mole. We can also look at the CH. What would you expect? Again, it would go with the hybridization. The sp3 has got more p character. Hydrogens are way out here, so that would be a longer bond. When your S grows, then you're going to get more and more spherical, and you're going to get closer and closer to the nuclei, so you would expect these to get shorter. But how about the bond strength? Is it going to be stronger here, here, or here? Let's look at it and see if you can come to some conclusion. The CH bond here is 1.10 angstrom, and it is shorter than a CC, and that's to be expected because hydrogen just has a 1s, so it can get really tight, close in. This is 1.08, and this is going to be 1.06. This is for the CH. This is going to be the sp2CH. Now, the bond strength, well, let's see, 98. It's even stronger than a CC. That's because the amount of overlap here is a lot. So almost like hugging it in. Here, CH is going to be even tighter because it's got more S, so it's closer to the nuclei. And here, it's going to be 125, so it's going to be even more. So the one thing you can conclude here is as the bonds get shorter, the energy to break it increases. So this is going to be inversely proportional to this. That's one thing you can conclude from the CC and from the CH. Same. Okay, no exceptions here. All right. Okay, so I know we always tell a rule and say, oh, this is the exception, but here, this is a case where we don't have any exceptions. So I'm sure you're going to be happy about it. Okay, so moving along, is there some way to predict how many double bonds there are going to be? Turns out there is a rule, there is a way, okay? That's called index of hydrogen deficiency. What does that mean? Well, look at this guy, he's only got 2. This guy's got 6. So it's compared to this, this is deficient. How deficient? 4 hydrogens deficient. Every time you take out 2 hydrogens, these 2 electrons, so you take off the hydrogen with the electron, these 2 electrons can hold hands and make a double bond. You take off 2 more hydrogens, you can make another double bond. So you see, 2 hydrogens indicate a double bond, lack of 2 hydrogens. So that's why we call it hydrogen, index of hydrogen deficiency. I'll write it over here, index of hydrogen deficiency. So if you had plenty of hydrogens and you drop a carbon in there, it's going to be saturated. This is the maximum. You cannot possibly put another hydrogen here because that's going to be breaking the octet rule. So you can't have 10 electrons over there. You can only have a maximum weight. This is maxed out. Can't put any more. That's saturated. In a saturated hydrocarbon, for every carbon, you have 2 hydrogens. If you, let's say you think of a long chain here, right? I'll just write it out and then maybe take it out. So let's say you have a long chain here. Every carbon is going to have 2 hydrogens on it. It doesn't matter how many. If you have 20 carbons, you'll have 40 hydrogens. If you have 30 carbons, you'll have 60 hydrogens because that's the way it is. Then at the ends, you go to cap it with 2. So for Cn, you have H 2 times plus the caps, the N carbons. Now over here, you took 2 off. Here, you took 4 off. So that's the hydrogen deficiency index. So for, I may have to skip this. So for CnHm, let's say, that's the formula. For every carbon, you'll have to have 2 times the number of hydrogens plus the cap plus 2. So that is going to be your formula for saturated. This is saturated. Anything else is going to have less. How much, we don't know, but we can put the hydrogens in and find out how much we can have less. So that hydrogen in that's already there is, let's say, Hm. This Hm. And for each 2 hydrogens, you can make a double bond, right? Every time you take off 2 hydrogens, those electrons can come together and make a double bond. So therefore, if you divide this by 2, that will tell you the number of double bonds. So that is going to be your index of IHD. And this is fine if you have just hydrogens. Now, let's say you have, instead of putting these 2 hydrogens here, you kind of wind them around like a garland and snap them together without these 2. We can also think of either doing a double bond, or you can think of how you could take those 2 off and make it into a cyclic compound here like this. Join these N carbons together and get a ring. And you will see 4, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. It has perfect octets all around. Okay, so therefore, when you have one hydrogen index, or when you have one IHD, you can either make a double bond or a ring. So this can be a ring or double bond. If you have 2 carbons, obviously you can't make a ring, but if you have 3 or more, then you can make a ring instead of a alkene. Now, one more thing, if you had a nitrogen or a halogen in here, let's say if you have a nitrogen or a halogen, which is like chlorine, bromine, or halogen, like you're just going to replace one of these hydrogens with a chlorine or bromine because that is also monovalent, just like hydrogen. Therefore, you're just going to add 1 hydrogen. add 1 to M. If you have a nitrogen that's an odd number, then you will subtract 1 from M. So that's something to remember when we do these. Let's keep going here and see if we can use this rule now to do the Lewis structures for this. So 4, 4, and 6, that's going to be 14 valence electrons. So let's do the valence electrons, bonding electrons, and lone pair according to the rules. No deviations. So here you're going to have 14, and so then you're going to put, well, who's going to be in the center? Who's the guinea pig here? Well, let's see, less electronegative, same rule, guys. Carbon in the center, and oxygen is the more electronegative. Tie it up, so tether all the other things. These hydrogens, so over here, if you do the 4 hydrogens, it's going to be 1, 2, 3. Can we put another one? Obviously not, because that will be 10, and this is second period, we can't exceed 8. So therefore, you're going to put that over here. So 2, 4, 6, 8, 10. And so you got 4 remaining lone pairs. Where are you going to dump them? Carbon already is saturated. So you can put them 1, 2, 3, 4. That's called an alcohol. Does the hydrogen deficiency index fit? Let's see. Cn, N is equal to 1, M is equal to 4 here, and H2N plus 2. So that is going to be 2 plus 2. That's 4. So that is going to be 4 minus, and you have 4 divided by 2, and that's 0. And that shows you there is no double bond over there. Let's move on over here. CH2O, carbon 4 plus 2 plus 6, that's 12. And carbon goes in the center, same deal as before, oxygen on the side. The hydrogen is written inside, so I'm not going to write it here, it's over here. And so that's 6 here, and we got 6 to play with. Where are you going to dump it? Can you put it on the oxygen? Let's see. First it says more electronegative atoms. So let's 2, 4, 6. That's all we have. We don't have, if we had 8, then I would have gone here. But I only have 6, and we have 6 for this oxygen. 2. When you're counting octet electrons, you count 2 electrons for the bond. But when you're doing formal charge, you count 1 electron. That's important. When you're counting octet, count 2 electrons per bond. But when you're counting formal charge, count 1 electron per bond. The lone pair would be the same. 2 when you count for octet, and 2 for each lone pair when you count for the formal charge. So, well, is this fine? Can we move on? Well, look at this, 2, 4, it's pretty obvious. 6 electrons here. So that's going to be 4 minus formal charge again. You only count 1 for each of this. 4 minus 3 plus 1. And over here, it should be 6 minus 6 in the periodic table, 7, so minus 1. Okay, obviously they're very unhappy. There is a solution for this. Minimize formal charges, make double or triple bonds. So obviously carbon's going to borrow from oxygen. Come over here, electrons. Keep me company here. So there you go. You have a double bond there, and you will have now 0 formal charge. These electrons moved over and made a pi bond. Does the hydrogen deficiency index fit? So for the Cn here, 1 carbon, so 2 times 1 plus 2 is 4, minus, well, how much do we have here? We have 2. Divided by 2, that is 1. So IHD is 1. And that's going to be a perfect fit here for this molecule because we do have a double bond. So IHD, Lewis structures, all falling into place now. Every one of this is a new functional group. Alkane, alkene, alkyne, alcohol, and this is a carbonyl group. This is an aldehyde, formaldehyde, but you can have carbons here, and it can be aldehydes or ketones. If you have a hydrogen and a carbon, it's aldehyde, carbon and a carbon, it's ketone, and we'll have a whole session on functional groups, so I'm not going to get into that much. Let's look at this molecule. We got a hydrogen in and a hydrogen out. What does that mean? Why are they like all over the place? Well, there is a reason it's out. It means hydrogens in front of the formula should be on an oxygen. That's something to keep in mind. Let's start with the IHD this time. CnH2n plus 2. So you have 1 carbon. So here we have 1 times 2 plus 2. That would be for the saturated. And we already have 2 here. And the whole thing is divided by 2. That's just part of the formula. That's your IHD. So here n is equal to 2, n is equal here to 1, and this is your n. N times 2 plus 2. So simple as that. So we only have 1 double bond, 4 minus 2 over 2. So we know that before we even write it. That's something we can keep in mind. Then we follow the rules. So least electron negative is carbon. Carbon has got 2 hands tied up with oxygen. Okay, good. And then there is a hydrogen in and a hydrogen out. Hydrogen in means it's on the carbon. Hydrogen out of in front means it's going to be on the oxygen. So the total valence electrons, sorry, we should have done this before, is 12, 13, 14, and 4, 18 electrons. And so 2, 4, 6, 8 electrons gone for that. We got 10 electrons to play with. Where do we dump them? Well, where else except the more electronegative atoms over here. We can't dump them in the hydrogen just because, you know, you can only have 1 arm, 2 electrons. So here we go. 2, 4, 6, 8, 10. Perfect. Distributed them all, but that means there's not enough to go on the carbon. Is everybody happy? Let's see. Carbon has 2, 4, 6. Obviously, that's really bad for carbon. Let's see. Let's see. Oxygen, it's got 8. That's fine. Let's do the formal charge. What's in the box? Same deal as before. If you box it up, just the element, whatever's in the box would be for that element for formal charge purposes. But in reality, these 6 electrons belong to carbon and they're sharing, but this is just a formality. It should only have 4 in the periodic table around it. 4 minus 3 is plus 1. So that's bad. And oxygen also, even though these are really shared equally between the two, for formal charge purposes, we take this as 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is -1, and we know the story now. We've done this many times. We're going to dump it in the middle, so the minus neutralizes the plus, and we get a very nice, beautiful neutral structure. And this is something that you love. This is your carboxylic acids that is part of your fat food chain. And here is your hydrogen. I'm just putting this in different colors because they're different functions. This CH is very strong. As you can see, CH bonds are pretty strong. They don't really come off. Kind of similar to an sp2. It could be different because it's with oxygens. And over here, this hydrogen is on an oxygen. It's going to pop off any time. So you had acetic acid. This is formic acid. These are carboxylic acid. So you have carbon with 2 oxygen and a hydrogen. That's called a carboxylic acid. So we're using your Lewis structures to also kind of get familiar with the structures of your functional groups. That's a carboxylic acid, and that's the most stable form, and not this. Okay, so let's keep moving over here and do a nitrogen. Let's do your index of hydrogen deficiency, IHD here. So 2n plus 2. So 2 times carbon is your n. So n is equal to 1 here. 1 times 2 plus 2 is 4. And over here we have m is 5. The m here is the actual hydrogens there, that's 5. And with nitrogen, subtract 1 from m. So here we go. So we subtract 1 from m. So that is going to be 4. And I'm just going to put that like this. Because you do this first, then you do this. The whole thing divided by 2. So this is 4 minus 5 minus 1. So the whole thing is going to be 0. Okay, so that means there's no double bonds in there. Let's put the carbon in the middle. And here is your nitrogen. Then that's the only other electronegative atom. Hydrogens then go all over the atom. First starting, put the hydrogen over here for the carbon, and that's 3. And then we have 2 more here, so we'll distribute them evenly like that. Let's look at the valence electrons, bonding electrons, and lone pair electrons. 2, so that's 8 plus 3 plus 5. 8 and 8, 16 electrons. So we have 16 electrons here. And let's draw it out and see what are the possibilities. 2 carbons here and a nitrogen. That's one way to do it. We can put the nitrogen in the middle. I guess why not? Carbon, carbon, and well, let's do it here, nitrogen. Well, this is pretty much the same thing as that, except it's bent. I mean, it's the exact same thing, but let's try something like this out. So this is, let's say, structure 1, structure 2, and there are a lot more possibilities. You can put the nitrogen in the middle and so on. But for rings, you don't have much choices because you need 3 atoms minimum for a ring, right? You can't have 2. So here's 2, 4, and then we have 3 hydrogens. Let's put them on over here. Hydrogens, well, you can spread them out. We can go in the corner. And I guess I have an agenda, so I'm putting it in the corner. But you can spread them out too. So this is 6, 7, 8, 9, 10. And there's 6 electrons, lone pair that we can play with. 2, 4, 6, 8. So nitrogen's fine as far as the octet's concerned, but everybody else is really unhappy. And this nitrogen has way excess charge. It should have 5, and it's got, let's say, 7. So it's a minus 2. Plus 2, really bad. So therefore, what can it do to alleviate all that charge? Same rule as before. Minimize formal charge by making double and triple bonds. So here you need 2 So you go over here and go over here. And that is a very, very, very common functional group called a nitrile. That's one structure possible. That's a nitrile. That's another possibility. This is what I mean. Carbon, carbon, double bond with a nitrogen, and we could have put that hydrogen here. That's a possibility. Why not? We could also, because that's all octet filled, and we have a lone pair here and a lone pair here. That's fine too. Or we could make a ring like this, put the nitrogen at the bottom. We have only 3 hydrogens. Well, distribute them evenly. Let's look at how that's possible. So here we go. 2, 4, 6, 8, 10, 12. So here, this is for structure 2. 16 minus 12 is going to be 4. So we can put 2 over here. We can't put any more because it's already got 8. Unlike here, this one's already got 3 things on it, right? So then where else can we put it? Should we dump it on one of the carbons? That will be -1 for that, +1 for that. Why make them both agonize over that electron? Just share it evenly and put 1 each and make it a deal, neutral. These are all possibilities for the same formula. So you have, again, multiple structures possible, and I'm not saying this is all there is, there can be more. When you have multiple structures possible and they're all correct Lewis structures, fulfilling all of the valence rules, and it's got all octets, they have a special name for this group, and that's called isomers. That's what we're going to lead to in our next video. Is going to be all about isomers, guys. This was just a little introduction how to do the IHD, and based on the IHD, then you can draw multiple structures for the same formula. That's called isomers. That's just like the textbook definition of an isomer. So just a few things about what we talked about, guys. If you have a saturated hydrocarbon that is straight chain, then for each of the carbons you have 2 hydrogens. Doesn't matter how long it is. And then you have 2 end hydrogens. So for CN, you have H2N and the caps. Now, if you take 2 of these hydrogens off, you can take those electrons and make a pi bond. So if you have an alkene, you will have that many hydrogens minus 2. So that is going to be CnH2n plus 2 minus 2, that's CnH2n. If you want to make a triple bond, you've got to take 2 of the hydrogens off and combine those electrons to make another pi bond. So it's this formula minus 2 hydrogens, CnH2n minus 2. And that's something you can apply for all hydrocarbons. Now, when you did the hydrogen index, we said about nitrogen and halogens. We didn't say about oxygens. If you have oxygens, you can just ignore them. You don't add or subtract hydrogens. One little thing before we conclude here, I'd like to say a little bit about the hybridizations of these functional groups or these molecules. Again, the way to find that is to count the number of sigma, that is the first bond between 2 atoms with the electrons being in the internuclear space. So if you have a double bond, you'll only count 1 for sigma. If you have a triple bond, you'll only count 1 for sigma. So the number of bonds in different directions, if you count them and also add the lone pairs to it, then each of those would need its own orbital, and so you would have to take S and any one of the 3 p's. Those are the 3. We don't usually go for any d orbitals like sp3, d2 and so on when you only have second period elements. If you go to sulfur and phosphorus and you have more than 4 bonds, then you can think of those. So just to look at these, Here, if you take either one of these carbons, you have 4 sigmas, 4 orbitals in 4 different directions. So that is going to be 4, and so therefore it's going to be sp3. Over here, again, as I said, the pi bond is really like a blob above and below the sigma bond. There's only one sigma bond in the internuclear distance. So the definition of a sigma bond is that the electrons are on the internuclear axis of the bond. And there's only one that can be in the internuclear axis because there's no space for 2. So therefore, this is going to be 3 directions and 120 degrees, and that's sp2. sp3 is going to be is in 4 directions, equal 109.5 degrees. Over here, this is going to be in 2 different directions. So therefore, 2 is sp. And if you look at carbon, this is just like that. If you take the oxygen, again, lone pairs have their own hybrid orbitals. So you have 2 sigma and 2 lone pair, and that's sp3. So even though this doesn't look like this carbon, it is an sp3, the same hybridization. The only difference is instead of having 3 hydrogens, it's got a hydrogen and 2 lone pairs. If you take this is the same as this. If you take the oxygen, again, 1, 2, 3 directions you have electrons. So therefore, it's going to be 120 degrees between this, where the lone pairs kind of push out. So you'd have a bigger angle here and a smaller angle here. Usually lone pair repulsion is greater than lone pair bond pair, and that's greater than bond pair. That's sp2. If you take this, it's the same thing. You can see 1, 2, 3 directions, sp2, 1, 2, 3, 4, this is sp3. And if you take this, sigma and 2 lone pairs, so that's going to be 120 degrees sp2. If you take the nitrogen here, you have 3 sigma and a lone pair, so this is sp3, and this one looks exactly like this, so it's sp3, it's 4 on there. If you have a triple bond again, if you take the nitrogen lone pair, you have a lone pair and a sigma in 2 different directions, and sp. So that's an sp orbital, hybrid orbital. So the lone pair is in an sp hybrid orbital, and the sigma bond in between is in an sp hybrid orbital. Same here, the lone pair is in an sp2, and the sigma is in the sp2. All right. So this is just a kind of a brief introduction to functional groups. We will talk a lot more about functional groups later. So stay tuned, guys, and I will see you soon.